My name is Joseph Wunderlich. I'm a professor of engineering, architecture, and computer science. This is an architecture lecture on wood, the second of 3. Share screen. We have the PowerPoint already open here. I'll show you the website or where to find this. You can look at that in other places. So this is the PowerPoint for this. Let's begin. Fix this display setting here. Okay. All right. So this is part 2. Heavy timber. So post and beam, mortise and tenon. Still done to this day. It used to be much more common in olden days. My farmhouse that students have seen, I've just put some new slides up last night of things I built over this summer. So hopefully not too redundant with some of these students have seen before. We have a garage, which is newer, but then the original house, 1877, a kitchen house, summer kitchen, that's called, or neighbors refer to it, and then a slaughterhouse, and then a barn, 1877. The barn, originally what it looked like before I started doing things to it, I've knocked all this down and built other things here. You see. This is still not exactly what it looks like now. I've put a big window here and taken down this stuff and built more structure. This is one of the first things I did was open it up and see the views. And so this is heavy timber construction. This is mortise and tenon. This is a lateral diagonal strut for holding up the building against wind loads. And then you'll see I've put more in recently. I'll go into details of that. And bracing added in 2000s for lateral stability. And you can see that here. 5,000 PSI concrete with anchor bolts, and then this heavy timber pressure treated. This is all new, and then lag bolted to this main structural support and column here, and then also sistering on a beam here, a girder to hold up the old barn, as well as a truss that I originally built over here when I first moved in. It's weathered, you can't really see it so much, and a new column, also anchor bolted into the ground. So here's that. Now these are lag bolted in here. These aren't mortise and tenon in. These are lag bolted in here, and this is lag bolted in here. You can see how that's done. The details of that. Here's an old mortise from an old tenon that was taken out, and all that was done. Well, this is on the other side of the barn. Similar thing, sistering it on some support. And so this is the barn. It used to be chickens above and large animals below. And this is what it looks like now. So you can see I took out this whole part of the barn over here and then put this cap on this wall here and made a picnic area out of it and built steps going up. I just did this not this summer, but the previous summer I did those steps. This is the upstairs of the barn, and I've taken down some of the ceiling and exposed some of the old post and beam up there. And then this is what it looked like. But before that, I took down this past summer, and I've opened this up and I've made it a great window. It's called here. There'll be a assignment in this course to do a great window. And this was really just a fun little project to make the barn a little nicer. And so I did this over the summer. This is my scaffolding. And so I set that all up. This is my daughter's little thing she used to wear where she'd go in the tub. Took a picture and sent her that in college just for fun. She's in college now. So scaffolding, got to be nice and secure. You can see the old structure and the new post and beam. And now it looks like this. Which I think is significantly nicer than the way it looked. And the old roof that had started collapsing, I took down. Now it's a nice picnic area. And so new beams again, bracing. This is my daughter a couple years ago. My son and our dog. And then you can look at videos here other times of timber frame barns. Students often in my classes make these. Balsa wood. And now the main house, main farmhouse, kitchen house, and the summer kitchen. That's what it looked like before I started building. And I've dissected all this, and it seems like they actually built all this at the same time. It looks patched on, but the way this structure interfaces, I have reason to believe they did it very soon, this one after that. This was an outhouse over here that I took off the back wall and built steps and filled in the outhouse. And there was no indoor plumbing originally in this building. Now there's 2 bathrooms and a third one underway. So again, this is where the old outhouse was, and then I built on a 1,500 square foot addition here. Main house. There's actually a window here. I put it in the shop. This is a shop area now. This was the addition. You can see here over top of the summer kitchen house and going into it. This was all stays the way it was. Although I have renovated some of the bathroom over here and this one, and with furniture and stuff. This is some of the old structure. So this is a 12-inch by 12-inch beam, and the old structure and a brick column. Somebody had shored this up before I moved in. This is something we'll talk about another. Well, there were some rotted beams here, and so there were new beams sistered on that was done before I moved in. And this is plumbing system we'll talk about in other courses. And so this is the old summer kitchen area. On my drafting table, there's a walk-in fireplace around the corner here. There were steps coming down here, and it looked like people lived above the summer kitchen in the winter. By the looks of it, that's our previous dog there. Okay, there's my daughter, who's now 20, and walk-in fireplace here. I just took this picture last night. We use it quite a bit now, and you can cook in here too if you need to. The brick for that. Stairs to the kitchen, out of attic house. So here you can get an idea of the old heavy timber framing, and then trying to interface with that, and doing that and transferring the loads around, shoring up the old building as I build the new heavy timber construction all around. The students in here can see over in the corner here that big member there was cut out of here. That was over to my right there, it was cut out of this section here. And you can see where I cut it off right there. And then heavy timbers here. I've now started a whole new bathroom over here, and this was tricky working this whole thing out here. You'll see in a second here how this weird roof and all this was dealt with. I don't teach at F&M. Somebody had worked at Franklin and Marshall. Apparently, I went to school there and painted this on the wall before I moved in 23 years ago. So this is tricky construction here to interface all this. There's part of the old roof of the old summer kitchen, the new roof that spans up over top of everything. The old beams, the old heavy timber beams. And then this whole mess here, I had to actually harvest the siding of here. And this is one reason it looked like they had built both houses at the same time, because this is really brand new siding once I peeled everything off that was under this roof that was over the summer kitchen, little piece of the roof. And so I had to harvest that to take out this temporary plug that I stuck in over here to fill in the awkward thing. Then I built up here and used that siding that was here and here. And this was like this. I just did this summer. I did this. Now this is actually an architectural thing. The real structure here is new wood, but I put this in coming out just to be in the context and the vernacular of this craftsman style. And it turned out pretty nice. So this is what it looks like now. So I put these windows in, put this siding, painted it. There was a tricky transition there to work with, because this is all brand new roof. This is old roof of part of one of the old buildings. And then it looks like this. It's kind of, I think, kind of a cool little thing. And then some of the casings inside trim work. We'll talk about this in the next lecture in woodworking or in finished carpentry. So this is all heavy timber, and then we'll look at rough and finished carpentry with traditional methods in the next lecture, the last of the 3 wood lectures. Girders carry beams, so these are beams carried by a girder. You can see it there. The old and the new married together. Just threw this in for fun. There's the shop back there. My son helping move gravel for the French drain to keep the water out. That's my daughter. I just sent her this picture last night coming in the shop. You can see the heavy timber there. This is my shop. There used to be a slaughterhouse. So I have a table saw, you can't see it in the foreground, a grinder, and a crosscut miter saw, compound miter saw, and various leveling and other equipment, and tons of other stuff. I put this window in 2 years ago in the shop that looks out over a neighbor's farm, a couple hundred cows, all Mennonite friends of mine, all Mennonite and Amish neighbors on all sides. Nice. There's another picture of that. So let's put that in. This is all heavy timber up here. Some new construction, heavy timber there, there, and there. And it's tricky, matching up the heavy timber with because you imagine that the dimensions are different here. So you're constantly tweaking things to marry the old actual dimension stuff to the nominal dimension new stuff. We repurpose wood. We save wood. Save wood. We make a table out of it. Also, we do in the septic system over here. Dug our own new drain field. And then there's some wood over here. We're saving, repurposing. My daughter just wanted to do a little project. That's one of my favorite pictures. Here's my favorite kitty, Little Miss, on the table that my son designed and made with our repurposed wood. And then some more heavy timber stuff. This is Japan and Kyoto, I believe we're in here, I think, or maybe it's Nagasaki, or not Nagasaki. And we were in Narita, went through Tokyo to Osaka. I was a keynote speaker in Osaka, and then we stayed over 2 weeks in Kyoto. This was Kyoto. More Kyoto, you see the heavy timber construction. They paint the ends to prevent rot. This one's all painted orange. Buddhist temple, Shinto shrines. And then the textbook that we're using has in it environmental impacts. And here you see a declaration for a building, an example, environmental building declaration for a University of Massachusetts building, 8,000 square feet. And they have, how much energy, 1,100 megajoules per meter squared, or in BTUs per square foot, if you like. And then, carbon sequestration, global warming effect, fresh water consumption. Structural considerations. So this is using glulam, or not glulam, but heavy timber and glulam. This is glulam up here. Let's stop sharing for a second here. Can I pause? I think I'm gonna, let's see here. I'm just gonna pause recording for a second. Okay, here's some books. So in 1983, I believe it was, I started my undergrad at Penn State, and then I transferred to University of Texas, both excellent schools in architectural engineering. But at that time, the building industry was booming in the South, or beginning to boom. And so I went down there. I had already done some renovation businesses, and I started my own business down there. And then I got involved with a lot of bigger buildings. And but anyway, so I was in Texas, and this is a course in structural engineering of just wood. So in the architectural engineering program, of course, you go calculus-based physics through differential equations and 3 physics courses, and then statics, of course, and dynamics, of course, strength of materials, of course, also material science as a course, and then indeterminate structures as a course. And then you take 3 courses in specific materials as wood design, steel design, and reinforced concrete design. And this was a wood design course. Dr. David Fowler, my advisor at Texas. And wood is more popular in the West. And all these steel, there's a steel design manual, there's concrete design manuals, and there's a wood design manual. So this isn't as common in the Northeastern schools to have a course in wood design, but we were in Texas, and not that there's a lot of wood structures in Texas, but there's more than the Northeast, and then the West has a ton of wooden structures, a lot of redwood things. So this was the design manuals we used. This had a wood book, 1980. And so now you build to the codes, of course, the building codes, but you also have design manuals which vary by the type of material. And so this is how you design for wood. And there's specific calculations and structural engineering course, as well as a textbook we had for design of wood structures. And so what you see now here is something out of our present book. And I'm familiar with doing these kind of things in class and a little bit in practice too, in San Francisco consulting firm, structural things. And it's very specific. Architects shouldn't be doing this kind of thing. This is for professional engineers to do. You're dealing with heavy loads and materials and fasteners that need to be very specifically controlled and designed. And especially if you're going up like this and this, British Columbia, I'm not sure the seismic loads there, but this is your diagonal bracing. You have either do moment connection or braced frame with your structural overall lateral loads. I mean, you do shear walls too, but to deal with lateral loads, especially in seismic areas, you either do this braced frame with these struts like this, or you make moment connections where you beef up the connections more, the moment connections, the torques, moments. It's more costly to do moment connection. When we're pricing buildings, it's in $1985, but working for developers in California, it was about $3 a square foot difference on commercial shell buildings and steel. Difference between brace frame but when you do brace frame, if you spend $3 a square foot less, which would be like $10 now a square foot less, then you have these struts in the way, and you can't charge as much for your renters. And these are speculative shell buildings where the tenants would move in and you give them so many dollars per square foot to build out. But so, this messes up square footage and views. It also makes it a little more difficult to build. Talk about that more in other classes. So this is heavy timber construction and different ways of putting together gusset plates and other things. The connections are always serious. That's normally where most things fail. You design for, as students, you're always designing for flexure and shear, and bending and compression and everything. But most failures, structural failures, you're going to see comes down to connections a lot. And I could talk about that for a while, but I'm not going to here. So, these are engineered connections. You don't want to do guessing at that. You need a structural engineer to do that, especially going up, and especially if you're in seismic areas. And so, this just all the different parts here, beams and girders, floors. There is an idea of the specific connection. So this would be a working drawing. Typically, architectural drawings are a tenth of the cost of structural drawings. Of working drawings, especially the structural, because you got to engineer it, and then there's a lot more sheets, and you're telling the builders exactly what to do, rather than just showing the aesthetics of it, which is not, I don't mean to minimize the aesthetics. That's actually what you're really trying to get the most for the client. But if you don't engineer it properly in detailed ways, people could die. And this is something that can be even more serious in masonry buildings, especially unreinforced masonry, but assuming this is reinforced masonry, these kind of connections can become critical because masonry can crack and chip, and this heavy load of a girder is sitting here, even though you're spacing it back. If you don't do this kind of thing right, this could fail very easily. Here's some ideas of how not to do things. So where you put bolts, again, this would be more for structural engineers to specify. You don't, as an architect, want to specify anything like this, because this is why engineers are engineers, is they take time to figure all these things out. And they're dedicated to doing just that. Typically, a structural engineer would be just doing structural engineering their whole life, and maybe just one kind, just wood or just reinforced concrete. And then you can trust that people won't die when they design stuff. That's the idea. So this is, how you have a column and two beams come together. Well, what about then going up a floor? Well, don't rest something like this on the wood. The wood will crush, especially if it weathers over time and moves around. This is a bad idea for transferring loads. So this is just something that an engineer, after enough years of practice, would know to do. They're doing that for a living. Different types of decking and heavy timber construction. Tongue and groove is always a good idea, as I mentioned before. Maybe that was the last lecture. But you want your connections to not be such that they can move around. And this gives you a nice tight connection, especially if you glue it. Although typically a lot of times you won't glue it because you do want it to move around to expand and contract under certain conditions, moisture and thermal changes. This is the building code, the International Building Code, and supporting roof floor loads and supporting roof loads only of different things, solid wood versus glue lam. There's a lot of detail there. And more detail here. This is fire resistance, and you have a rating of so many hours per partitions. The fire marshal will inspect drawings, especially in California, but everywhere actually now, where you have to prove that your building will won't kill people when it catches on fire. And so you have places that it can escape readily, get out of the building, access points, as well as materials that will take a certain amount of time to burn, so the place doesn't collapse right away and the fire doesn't spread too fast. And then a couple different methods of doing that. Wood will actually char and then stop burning. So you can put a encapsulated material that will burn first, and then once a big heavy timber chars, it will stop burning for a while. So you can build that into your hour rating of how many hours of given member is. You see this with steel too, with not fire. Actually, steel will melt at a certain temperature, unfortunately. But you see this with rusting steel. Steel will rust, and then it'll stop rusting. So you can design steel so that there's the outer part rusts a certain amount, and then you're relying on the non-rusted part to carry the load for the life of the building. Same kind of thing with fire, sort of. And then here's different panels, cross-laminated timber. This is becoming more popular. Big, heavy timber trusses. Some more complicated ones. And that is that. Okay. Stop sharing. And